A star can spend millions of years calmly fusing atoms, and then, one day, it just absolutely loses it and collapses into a hole in reality. Not a hole like, oops, dropped my keys, a hole where space itself says, yeah, we're done here. So what kind of cosmic bad day turns a giant ball of fire into the universe's most aggressive vacuum cleaner? Turns out, it's less about burning out and more about gravity finally winning the ultimate arm wrestling match. A star doesn't explode into a black hole because it's feeling a little tired. It does it because gravity finally wins the most dramatic tug-of-war in the universe. For millions of years, a star is basically a giant nuclear reactor, fusing atoms in its core and blasting energy outward, which acts like a cosmic anti-gravity force. That outward pressure keeps the star puffed up, like a balloon that refuses to pop. But here's the twist. The fuel runs out, and when that happens, the outward pressure just stops showing up to work. Gravity, which has been patiently waiting this whole time like a bouncer at closing time, suddenly takes over and says, all right, party's over. For really massive stars, like at least 20 times the mass of our Sun, this collapse is not gentle. The core shrinks faster and faster, compressing matter into a smaller and smaller space until the density becomes absurd. We're talking about cramming the mass of a star into something smaller than a city. At that point, physics basically throws its hands up and says, we'll call this a singularity, and move on. That's the moment the star has its full-on meltdown, no graceful exit, just a total gravitational collapse into something so dense that not even light can escape. It's less like burning out, and more like the universe hitting the cosmic delete key. Before a star turns into a black hole, it doesn't go quietly. It throws one of the biggest explosions in the universe, like a dramatic farewell tour nobody asked for. As the core collapses inward, the outer layers of the star don't just politely follow, they bounce. The collapsing core becomes so dense so quickly that it creates a shock wave that blasts outward, ripping the star apart in a supernova explosion. This is not a small event. For a brief moment, that single star can outshine an entire galaxy. Imagine one light bulb suddenly becoming brighter than billions of others combined. That's the level of drama we're dealing with. And while it looks like destruction, it's actually a creative process too. All those heavy elements, iron, gold, even the stuff in your phone get forged and scattered into space during this explosion. So yes, your existence is partially the result of a star having a catastrophic breakdown billions of years ago, which is both poetic and slightly concerning. But here's the key part. The explosion doesn't always completely destroy the core. If that leftover core is massive enough, gravity keeps crushing it even after the blast, ignoring all that dramatic flare, and continues the collapse into a black hole. So the supernova is basically the universe saying, watch this, right before the real transformation happens. There's a very specific moment when a collapsing star crosses the point of no return, and it's not marked by fireworks or a dramatic soundtrack, it's defined by math. As the core keeps shrinking, its gravity becomes stronger and stronger, until it reaches a threshold where the escape velocity exceeds the speed of light. And since nothing in the universe is allowed to go faster than light, that means absolutely nothing can get out, not particles, not radiation, not even a desperate last text message. This boundary is called the event horizon, which is a very polite scientific way of saying anything past this point is gone forever. If you were watching from a safe distance, you'd never actually see anything cross it. Objects would just appear to slow down and fade away, like the universe buffering at the worst possible moment. Inside that boundary, all the mass continues collapsing into an incredibly tiny, dense region we call a singularity, where our current understanding of physics basically breaks. It's like reality itself shrugs and says, I don't know what's happening in there, and I'm not going to pretend I do. So when we say a star becomes a black hole, what we really mean is that it has collapsed so completely that it creates a region of space where escape is impossible. A cosmic one-way door with no returns, refunds, or exceptions. Here's the thing. Not every star that runs out of fuel decides to go full black hole mode. Some stars have just enough self-control to stop short of total collapse. When a star's core compresses, there are quantum mechanical forces that push back, like tiny particles refusing to be squeezed any closer together. In smaller stars, this resistance is enough to halt the collapse, leaving behind a neutron star a super-dense object where atoms are crushed into neutrons, but not all the way into a singularity. It's like the star had a breakdown but still managed to keep it somewhat together. But if the core is too massive, roughly more than about 2 to 3 times the mass of our Sun, even those quantum forces get overwhelmed. Gravity just steamrolls everything, ignoring all protests, and keeps collapsing the core beyond the neutron star stage. That's when you get a black hole. So, really, black holes are what happens when a star is too big to stabilize itself. It's the difference between a dramatic sigh and flipping the entire table. The universe has thresholds, and crossing them turns a bad day into a permanent disappearance. Black holes have a reputation for being invisible, which is technically true, but ironically they're often surrounded by some of the brightest stuff in the universe. As the star collapses and forms a black hole, any leftover gas and debris doesn't just fall straight in like water down a drain, it spirals. This swirling material forms what's called an accretion disk, and as it spins faster and faster, friction heats it up to extreme temperatures, causing it to glow intensely in X-rays and other high-energy radiation. So while the black hole itself is completely dark, no light escapes, the stuff around it is basically screaming, "Look over here!" It's like the black hole is hiding in a spotlight made of its own leftovers. And if that weren't dramatic enough, some of these systems even shoot out jets of particles at nearly the speed of light from their poles, powered by magnetic fields and rotational energy. So you've got this invisible object surrounded by a glowing disk and blasting jets across space. It's less like a quiet disappearance and more like a cosmic rock star refusing to leave the stage. The irony is perfect. The most invisible things in the universe are often the easiest to spot because of how violently they interact with everything around them.